Hello everyone, my name is Amir Mohammad Naseri and uh, I'm going to present our paper entitled Encrypted Cloud-Based Set-Theoretic MPC. Other authors of paper are Dr. Walter Lucia and Dr. Omar Youssef from Concordia University. This is the outline of this presentation. As you know, model predictive control is one of the popular control strategies to deal with constraint control problems. Standard MPC uh, is based on solving an optimization problem in a reciting horizon fashion. But sometimes there is not enough computational power to solve this optimization problem on the plant. So in this case, we can use cloud servers to solve this optimization problem. In this case, privacy of the information transmitted to the cloud is an important concern for us. So recently, many solutions have been proposed in the literature to solve this problem. One of them is using homomorphic encryption and the concept of encrypted control systems. Such solution can be easily deployed for static feedback controller, but it is a bit challenging for optimization-based control strategies like MPC. Encrypted model predictive control has been investigated in the literature and many solutions have been proposed. But in general, we can categorize all these solutions into two categories. The first one is using just single cloud and the second one is using multiple clouds. Since using multiple clouds need expensive infrastructures, so in this paper, we just focus on using single clouds. The existing solution in the literature for using single cloud have the following limitations. First of all, to reduce the computational demand on the actuator or sensor, input and state constraints are assumed to have simple shapes, like box-shaped constraints. And the other limitation is the computational capabilities of the sensor and actuator is not taken into the account during the design stage. In the following slides, I'm going to review some background material to understand this presentation better. First of all, we have homomorphic encryption. Homomorphic encryption is a class of cryptosystem which allows to perform some basic mathematical operations on encrypted data. There are different types of homomorphic encryption with different properties. Some of them are, for example, additive homomorphic encryption, when we can define an operator between two encrypted data and find addition of these two, like equation number 1. Then we have multiplicative homomorphic encryption. In this case, we can define another operator to find the multiplication of M1 and M2, like equation number 2. And also, some of homomorphic cryptosystems, like failure, has the property to define an operator between a plain text and an encrypted data and find the multiplication of these two, like equation number 3. We also have proximal gradient method. PGM is a technique to solve optimization problem in the format of equation number 4, where f and g are closed proper convex function and f is differentiable. We can define the PGM operator like equation number 5, where alpha is the step size. And in this case, we can find the solution of equation number 4 by solving equation number 6 iteratively. And the last one is a set-theoretic MPC, which is a specific type of model predictive control. It has two different phases. The first one is offline phase. In the offline phase, first we should find a state feedback controller and its associated robust control invariant region with satisfying all the constraints, which is this green region here. Then we can enlarge the domain of interaction of this region by building this one-step controllable sets until it covers the desired region. For example, in this case, we built 4 to cover the initial state of the system here. Then we have the online phase. In the online phase, first of all, we should find the smallest index which the state of the system belongs to. Then based on this index, we can take different actions. If the index is 0, which means we are in the terminal region, we can apply the designed state feedback controller. Otherwise, we should solve this optimization problem in equation number 9, which is the standard MPC optimization problem. But in here, the prediction horizon is equal to 1. Set-Theoretic MPC also satisfy the following properties. First, the smallest RCI region, or tau 0, is reached at most in n steps, regardless of any admissible disturbance realization or cost function, and capital N is the number of one-step controllable sets. Also, stability and recursive feasibility are ensured regardless of the disturbance and the cost function. In the following slides, I'm going to explain the assumption that we have for solving the problem in this paper. We consider a network control system, like equation number 10, with a bounded disturbance. Also, we have an additive homomorphic encryption, which supports the multiplication between a plain text and an encrypted data like failure. And also, we assume an honest but curious cloud, which means that the cloud doesn't deviate from the control logic, but can eavesdrop on the transmitted information. And also, the actuator of the system can perform simple arithmetic operations. So we're going to design an encrypted set-theoretic MPC with the following objectives. First of all, we want the controller to be implemented on the cloud. Second, we want this strategy to enjoy the same properties as same theoretic MPC. And also the number of arithmetic operations required to be performed on the actuator side should be designed to be real-time affordable by the available hardware. To achieve the mentioned objectives, we have a couple of challenges that I'm going to explain. The first challenge is how to solve this optimization problem, which is the set-membership optimization problem for the first step of the set-theoretic MPC in encrypted form. Our solution to this challenge is to start from the largest member of the family of robust one-step controllable sets. Because these sets are nested, so for sure, the initial state of the system belongs to the largest one. So this is the first challenge. The second challenge is how to solve the constraint optimization problem in encrypted format. The optimization problem in equation number 13. So to solve this optimization problem, we're going to use proximal gradient method, as I mentioned before. In proximal gradient method, the function f in our case corresponded to the cost function, and function g corresponded to an indicator function defined over the set UI. And this set UI is the combination of a state and input constraint with the dimension of f tilde I plus fu. So this is how we can solve the original optimization problem with PGA. So in our case, since g is corresponded to an indicator function, then we can write this proximal gradient method operator like equation number 18, which is a projection or on the set UI. So this projection cannot be done in encrypted format, so we should send it to the actuator and do it in plain text. But how we can make this projection affordable for the actuator? Our solution is, instead of solving an optimization Euclidean projection problem, we can do it iteratively with a recursive solution, which is explained in equation number 19. in which the number of operations required to do the projection depends on the number of inequalities we need to show the uh, set of constraint, which is in this case f tilde I plus a few, the number of faces we have for this set. Now the question is, can we control the number of faces, which means f tilde I plus a few, to describe the set UI or not? The solution is using a zonotope instead of polyhedral set. So what is a zonotope? A zonotope is a convex polytope which is defined by a center like C and a set of generator vectors in equation number 20. So the number of half spaces or the number of faces we need to describe each robust one-step controllable set in the format of the zonotope is upper bounded by 2 to the power of p, where p is the number of generator vectors, which is a trivial upper bound, and also if p is bigger than n, where n is the dimension of our space, then we can define this upper bound for the number of faces we need to describe a zonotope. So by exploiting the zonotope inner approximation of a polyhedral set, the recursive definition of robust one-step controllable set can be modified as equation number 21, where psi I minus 1 is an inner approximation of tau I minus 1. So we can to find this zonotope inner approximation, we can use this equation number 22, which is taken from this paper. In the following slides, I'm going to explain our simulation setup and our simulation results. As a simulation setup, we consider a two-tank system, which has two different states, which are the height of the water in the tanks, and three different control inputs, which are the voltage of these valves, one on top and two in between of the tanks. We use EC-lib to implement failure cryptosystem when we consider P and Q 1024 bits. By using the equations of the two-tank system and finding the linear equation and discrete equations of the system, when the sampling time is 1 second, we end up with these matrices A and B to describe the system. And also, we consider these input and state constraints for the system in the presence of the disturbance, which is bounded to this value. We also assume that the actuator of the system is capable of performing 12 iterations of half-space projection in one sampling time. We should spend 6 of these 12 iterations for projection into the input constraint, because we have 3 inputs and a box-shaped input constraint, so we need 6 out of 12 to project into the input constraint. And we just have 6 to perform the state constraint projection. So we can choose the number of generator vector for zonotope inner approximation to have an upper bound of 6, which should be 3 generator vector, and this is the upper bound we have, which is equal to the number of maximum number of operations can be performed in the actuator. In this slide, we have the set membership index of the state of the system at each time step. The yellow curve is the original Set-Theoretic MPC. The red one is our proposal, the encrypted mode. When we consider that the state of the system belongs to the largest one and at each step, we move just one step forward. And the blue dashed line is just the actual state of the actual index which the state of the system belongs to in our proposed model. In this slide, we have the trajectory of the state of the system. The red one is the original Set-Theoretic MPC, and the dash blue line is our proposal. Uh, we reach to the terminal region with a suboptimal solution, but you can see that all the state constraints of the system are preserved and the control and the properties of Set-Theoretic MPC are satisfied. And these are the control inputs of the system in original Set-Theoretic MPC and our proposed model, which is obvious from the figure that all the inputs constraints are satisfied. As the conclusion of our presentation, we proposed an encrypted set-theoretic model predictive controller for a single cloud network control system. By taking advantage of zonotopic approximation of robust one-step controllable set, we can design the maximum number of operations required on the actuator. And we prove that all the properties of set-theoretic MPC control are preserved. Thank you for your attention, and these are some of the main references of this paper.